In this video, we present a framework for reasoning and making decisions in environments made up of selfish agents. We also provide early results of the behavior of the framework through simple trading scenarios. The framework, which we call RepNet-MDP, is based on RepNet-MDP, a framework published by Rens in 2018. We can make out key elements of the framework. The notation is heavily inspired by the syntax of standard Markov decision processes, but instead of dealing with a single agent deployed in a static environment, as in standard MDPs, the new framework considers dynamic environments made up of several autonomous agents. The agents are assumed to be selfish, and the interactions between agents are assumed to be driven by their reputation in the network. How does the new framework fit within the current literature? Multi-agent learning techniques such as multi-agent deep reinforcement learning are now commonly used in practice and generally produce good results. However, these techniques come at the expense of interpretability of the results. Distributed systems, which involve notions of trust and reputation, often require decisions made by an AI to be explainable. While reputation systems have become common in e-commerce platforms, peer-to-peer file-sharing systems, and other distributed systems, they are often specific to the problem at hand. We propose a framework that deals with agent behavior and transition probability uncertainties in a systematic way. Let's spend a few moments on building an intuition for the RepNet framework. As a reminder, the standard MDP is made up of the following elements: a static environment in a given state, an autonomous agent that acts upon the environment, after which the environment transitions to a new state, returned to the agent. Optimal behavior in each state is dictated by the following recursive equation, called the value function. The most common extension to MDPs, called partially observable MDPs, introduces the notion of partial observability of the environment. Instead of returning the actual state of the environment returns a local observation. This observation contains information as to the actual state of the environment. We can extract this information and store it in what is called a belief state. Upon reception of a new observation, this belief state is updated through a function called the state estimation function. Now, in RepNet-MDPs, the environment is not static. Instead, it is made up of several autonomous agents assumed to be self-interested. At each time step, the actual state of the environment is returned to us. That is, we do not need to extract this particular information from a local observation. But the state can tell us other things. For one, it tells us how the agents of the environment are likely to behave. In essence, if the agent had the tendency of acting a certain way in a given state, it is likely to do so again in the future. We store the behavioral habits of each agent in what we call the action distribution. Additionally, the state informs us of the image all agents have of each other. That is, if an agent does not interact with another agent despite the potential benefits of that interaction, it most likely has a poor image of that agent. Finally, we can summarize the individual image values, and for each agent produce a separate numerical value that describes their reputation. Let's now go over optimal behavior for RepNet-MDP agents. Recall that in standard MDPs, optimal behavior is derived from the following recursive function v. It is a function of the state of the environment. The part of the equation highlighted in blue describes the transition model of the environment. Highlighted in green is the immediate reward obtained by the MDP agent in state S upon taking action A. The RepNet-MDP value function has a lot of similarities with the MDP function. In addition to being a function of the state of the environment, it is now also a function of the action distribution and the image. The immediate reward is now also a function of the action distribution. We refer to the full paper for details on the internal workings of this function. The new transition model is a function of the image. We call this transition model the subjective transition model. More on that in a bit. In this work, we use an online planning strategy to find approximate solutions to RepNet-MDPs. Basically, online planning consists in alternating between two phases, the planning phase and the execution phase. Given the current state of the environment, say S1, a look-ahead search tree of potential futures can be constructed. Then, starting at the bottom of the tree, we can backpropagate estimates of the value function. Upon arriving at the top of the tree, we select the action associated with the highest value, which in this case is given by A1 star. This action is then applied to the environment, which then returns a new state of the environment, here as 2. The same process is repeated from there. RepNet-MDPs distinguish between two types of transitions: objective transitions and subjective transitions. Let's explain the difference. The objective transition model describes the actual rules of the environment. In other words, it describes the usual transition probabilities we know from standard MDPs. When an action is applied to the environment, the transitions of the environment are dictated by this transition model. But before applying an action, the RepNet agent needs to determine the best course of action by constructing a look-ahead search tree and using the value function. This value function incorporates the concept of subjective transition model. This transition model has an additional parameter, namely the reputation of the RepNet agent. The model does not describe the transition rules of the environment, but the influence that the RepNet agent's reputation has on the outcome of certain transitions. For instance, a trade between two agents is more likely to be successful if the agent making the trade offer has a good reputation. This additional parameter makes it possible to account for the RepNet agent's reputation while planning. We can now discuss the early results obtained on a simple trading scenario between 3 agents. In this experiment, Agent A is the RepNet agent. Agents B and C both have predetermined courses of action. The goal of the experiment is to evaluate Agent A's behavior based on the behavior and reputation of the other agents. In the first phase, Agent B is asked to reject all trade offers, while Agent C is asked to accept all trade offers. The RepNet agent is able to successfully adapt its own behavior by using the action distribution and the image function, and ends up conducting the majority of its trades with Agent C, as can be seen in the bar plots. In the second phase, Agent B and Agent C's roles are reversed. Agent B is now expected to accept all trade offers, while Agent C is now expected to reject all trade offers. We can see that the RepNet agent is able to unlearn its previous behavior and ends up conducting the majority of its trades with Agent B. In the final phase, Agent B and Agent C's roles are switched back to what they were in the first phase. However, unlike in the first phase, the RepNet agent does not interact with Agent B or Agent C, but simply observes the interactions between Agents B and C. Agent B's reputation decreases and Agent C's reputation increases, and as a result, we might be expecting that the RepNet agent wants to trade with Agent C. However, as per the bar plots, this is not the case. We conclude that, in the framework's current formulation, a RepNet agent is incapable of inferring new behavior from interactions in the network when these interactions do not directly involve the RepNet agent. We refer to the paper for a potential way of addressing this issue. In conclusion, we stress that the results obtained so far have the main intention of serving as a proof of concept for the framework. This work does not address the scalability of our approach to problems of realistic size. A compact way of representing state spaces, such as a relational representation, may be a first step in overcoming the inherent complexity of real-world problems. Finally, the functions for updating the action distribution and the image have complicated formulations and may benefit from being simplified. That is all for this presentation. Thank you for listening, and I invite you to read the whole paper for more details.